black smoke billowed from German fighters as they spiraled earthward. The date burned into history books would be March 6, 1944. Nearly 6 miles above Berlin, American pilots witnessed something that would shake the Luftwaffe to its core. German fighters attempted their proven escape tactic. They pulled hard into climbing turns, racing toward the thin air where heavy American fighters had never been able to follow. For over a year, this maneuver had saved countless German lives. But today felt different. American Thunderbolts clung to their tails through impossible climbs. At 28,000 feet, where engines gasped for oxygen and wings struggled for lift, P-47 pilots squeezed triggers. Bullets found their marks. German pilots abandoned burning aircraft, parachutes blossoming against the pale sky. The 56th Fighter Group tallied 11 kills. Not a single Thunderbolt was lost. Something fundamental had shifted in the balance of air combat over Europe. The transformation traced back to a seemingly simple modification that had taken American engineers 9 months to perfect. Winter 1943 had been brutal for American air crews. Bomber formations bled aircraft over German industrial targets, while fighter pilots filed increasingly desperate reports. The same story repeated mission after mission. German fighters would dive through bomber formations, attack with devastating effect, then climb away to safety. American escorts watched helplessly as enemy fighters escaped into vertical maneuvers no P-47 could match. The Pratt & Whitney R-2800 engine generated 2,000 horsepower. Yet the massive Thunderbolt climbed like a pregnant elephant. This contradiction puzzled engineers until they examined the aircraft's narrow-bladed Curtiss electric propeller. Those knife-thin blades were optimized for high-speed efficiency. Above 350 miles per hour, they sliced through air with minimal drag. But during climbs, when airspeed dropped and pilots needed maximum thrust, the narrow blades couldn't grab enough air to convert horsepower into vertical performance. Engines screamed at maximum RPM. Fuel burned at alarming rates. Heat gauges climbed toward red lines, but aircraft wallowed upward with agonizing slowness. At Republic Aviation's headquarters on Long Island, Alexander Kartveli studied combat reports with growing alarm. German Focke-Wulf 190s and Messerschmitt 109s reached combat altitudes far more quickly than his Thunderbolts. This performance gap was measured in American lives. The solution appeared deceptively simple. Propeller efficiency depended on matching blade area to operating conditions. Narrow blades worked well at high speeds. During climbs, blades needed more surface area to grab air and convert power into thrust. But propeller design affected every aspect of aircraft performance. Wrong blade shapes could create vibrations that would tear engines from their mounts. Improper weight distribution might generate harmonics, causing catastrophic structural failure. Incorrect torque characteristics could make aircraft uncontrollable during takeoff. Republic needed propellers with dramatically increased blade area that could integrate into existing aircraft without extensive modifications. 2 companies competed to solve this life-and-death engineering puzzle. Curtiss-Wright, manufacturer of the original narrow-blade propeller, faced off against Hamilton Standard, producer of propellers for numerous military aircraft. The winning design would be manufactured in quantities exceeding 10,000 units. More importantly, it would determine survival rates for thousands of American pilots flying into German-controlled airspace. Engineers at both companies worked through the bitter winter of 1943. Wind tunnel tests ran around the clock. Stress calculations covered blackboards. Prototype hubs and pitch control mechanisms took shape in machine shops. American pilots were dying while engineers refined blade chord lengths and twist angles. Hamilton Standard's team developed a radical departure from conventional propeller design. Instead of thin, knife-like blades that sliced through air, they proposed wide paddle-shaped blades that grabbed air like oars pushing through water. Blade chord would increase dramatically. Blade shape would be almost rectangular for much of its length before tapering near the tip. This design looked crude to engineers trained in traditional aerodynamics. Wind tunnel tests revealed remarkable results. The design generated significantly more thrust at low air speeds while sacrificing minimal top-end performance. Curtiss-Wright countered with their own wide blade design, maintaining a more traditional elliptical blade shape but dramatically increasing overall area. The Curtiss design featured blade cuffs at the root that smoothed airflow into the propeller hub and reduced vibration. Both designs represented massive improvements over original narrow blades. Republic Aviation received prototype propellers from both manufacturers in April 1943. Testing began immediately at Republic's facility and at Wright Field in Ohio. Test pilots evaluated both designs systematically. Both the Hamilton Standard and Curtiss propellers offered nearly identical performance improvements. Climb rates improved dramatically with either design. Hamilton Standard offered slightly smoother operation due to hydraulic pitch control. The Curtiss design integrated better with existing aircraft systems and would be easier to retrofit to P-47s already overseas. Neither was clearly superior in all categories. The Army made a pragmatic choice driven by manufacturing capacity. Both would be approved for production. This decision prioritized rapid deployment over lengthy evaluation to determine theoretical superiority. Hamilton Standard propellers would fit new P-47s built at Republic's Farmingdale facility. Curtiss paddle blade propellers would fit P-47s built at the Evansville, Indiana factory and be supplied as retrofit kits for earlier aircraft in England. The dual-source strategy would also complicate German intelligence efforts. Production began in June 1943. Manufacturing and testing delays meant first operational aircraft did not reach England until late December 1943. Throughout December, P-47s were flown to RAF Wattisham, where mechanics retrofitted them with new propellers. The 56th Fighter Group, flying from Boxted in Essex, completed transition by early January 1944. Group Commander Lieutenant Colonel Hubert Zemke immediately recognized tactical implications. Dramatically improved climbing performance meant his pilots could engage German fighters using vertical tactics that had been suicidal with narrow blade propellers. Zemke organized intensive training through January 1944. He developed new combat procedures specifically designed around the paddle blade Thunderbolt's enhanced climbing ability. He taught pilots to engage German fighters in climbing spirals, maneuvers that previously would have left them vulnerable. He developed techniques where pursuing P-47s would pull up sharply if enemy fighters tried to climb away, convert speed into altitude, then dive back onto targets with accumulated energy. With narrow blade props, these maneuvers would have left Thunderbolts wallowing at low speed. With paddle blades, they became deadly offensive tactics. January 4, 1944, marked a significant milestone. The entire 56th Fighter Group flew its first mission, with all aircraft equipped with paddle blade propellers. Pilots immediately noticed the difference. Aircraft climbed with an eagerness that seemed impossible for 7-ton fighters. Energy retention in vertical maneuvers improved dramatically. Thunderbolts could now follow German fighters into climbing escape maneuvers without losing position. The real test would come when they encountered the Luftwaffe over Germany. Combat debut came during escort missions in late January and early February 1944. American fighters encountered situations where German pilots executed standard escape tactics, only to discover pursuing Thunderbolts matching their climbs. Initially, German pilots assumed they faced a new American fighter type. When intelligence officers examined gun camera footage clearly showing standard P-47 Thunderbolts achieving this performance, confusion spread through Luftwaffe units. How could the same aircraft they had successfully evaded for months suddenly match their climbing performance? The Brunswick mission provided dramatic confirmation. Lieutenant Colonel Zemke led 48 Thunderbolts on bomber escort, routing over Berlin. Luftwaffe controllers vectored more than 80 Messerschmitt 109s and Focke-Wulf 190s toward the incoming bombers. As bombers approached at 24,000 feet, German fighters attacked using standard tactics. They dove through formations, then pulled into steep climbs to escape escorts. Across the sprawling battle, Thunderbolt pilots matched German fighters in vertical combat for the first time. Captain Robert Johnson caught climbing Messerschmitts and destroyed them at high altitude. Lieutenant Walker Mahurin engaged Focke-Wulfs in vertical maneuvers that should have been impossible for Thunderbolts. Other 56th Fighter Group pilots discovered they could contest any climbing engagement. The group claimed 11 victories without losing a single Thunderbolt. More importantly, not a single bomber in their formation was shot down. German pilots landing after the Brunswick mission reported disturbing developments. American Thunderbolts were climbing with them. Multiple pilots insisted they must have encountered a new fighter type. When shown gun camera footage depicting standard P-47s achieving described performance, confusion deepened. Luftwaffe technical intelligence needed to understand what had changed. The first clue came from wreckage analysis in early February. A shot-down P-47D-23 was transported to the Luftwaffe test facility at Rechlin. Engineers examining the aircraft immediately noticed the propeller. Blades were far wider than those on previously captured Thunderbolts. The technical intelligence report described the new design, but initially failed to grasp its significance. They concluded the modification likely improved takeoff performance rather than combat capability. This misunderstanding cost the Luftwaffe valuable time. Throughout February 1944, more P-47 groups transitioned to paddle blade propellers. The 4th Fighter Group received theirs in early February. The 78th Fighter Group completed transition by mid-February. By month's end, 6 of 8 Thunderbolt groups in England flew paddle blade-equipped aircraft. Each group immediately saw improved combat effectiveness. German fighter losses climbed as Luftwaffe pilots found standard escape tactics no longer worked. On February 21, 1944, Jagdgeschwader 26 lost 7 Focke-Wulf 190s in a single engagement with the 56th Fighter Group. Unit Commander Major Klaus Mitusch filed an after-action report revealing frustration. His pilots had engaged according to established doctrine. They disengaged through climbing attacks when pressed. Every pilot who attempted this maneuver was shot down. Mitusch requested immediate clarification on whether Americans had introduced a new fighter type and whether existing tactical doctrine remained valid. Luftwaffe intelligence had no satisfactory answer. German understanding improved through observation and wreckage analysis. By March 1944, Luftwaffe intelligence recognized that American engineers had modified the Thunderbolt's propeller to improve thrust at low airspeeds, particularly during climbs. Reports circulated warning that American fighters could now contest vertical combat. They recommended engagement only when holding clear energy advantage and disengaging through level high-speed flight, rather than climbing escape. But changing tactical doctrine across hundreds of fighter squadrons proved impossible. Pilots who had survived by climbing away for the past year could not instantly reprogram survival instincts. The transformation's scale became undeniable during Big Week. The massive bombing campaign against German aircraft production facilities in late February 1944. From February 20 to 25, the 8th Air Force launched over 3,800 bomber sorties, escorted by more than 3,600 fighter sorties. The vast majority of American fighters were paddle blade-equipped P-47s. The Luftwaffe launched over 2,000 sorties in defense. Germans lost approximately 355 fighters, destroyed with another 100 damaged beyond repair. American fighter losses totaled 28 aircraft. The exchange ratio had shifted dramatically. Thunderbolt pilots discovered that paddle blade propellers created opportunities beyond simple climb performance. Increased thrust at low speeds improved acceleration out of dives, allowing Thunderbolts to build energy faster after high-speed attacks. Pilots could execute dive and climb attacks repeatedly, maintaining initiative throughout extended engagements. Improved thrust also enhanced turning performance at slower speeds. While Thunderbolts still could not outturn Messerschmitt 190s or Focke-Wulf 190s in flat horizontal turns, they could maintain sufficient energy in climbing turns to prevent German fighters from gaining angular advantage. Major Francis Gabreski, commanding the 61st Fighter Squadron within the 56th Fighter Group, became the leading proponent of what pilots called the climbing spiral. Gabreski would engage a German fighter at co-altitude, typically around 24,000 feet. Rather than attempting to outturn the enemy horizontally, he would maintain speed and pull into a climbing turn. German pilots, seeing the Thunderbolt climb, often followed, expecting the American fighter to lose energy and become vulnerable. But with paddle blade propellers, P-47s maintained climb rate even while turning. Gabreski would spiral upward through 2 or 3 full circles, gradually reducing the German fighter's energy state until the enemy stalled or was forced to break off. At that moment, with the German fighter at low speed and high altitude, Gabreski would reverse, dive onto the target, and open fire from a position where the enemy had no escape route. Gabreski ultimately claimed 28 aerial victories flying P-47 Thunderbolts, making him the leading American ace in Europe flying a single aircraft type. Nearly all these victories came after his squadron transitioned to paddle blade propellers. In post-war interviews, Gabreski consistently credited the new propeller as the single most important factor in the P-47's transformation. The modification required minimal changes to pilot training. Aircraft simply did what pilots wanted, maintaining energy in situations where narrow blade-equipped Thunderbolts would have failed. The paddle blade program represented American industrial capability operating efficiently. From initial concept to widespread deployment required only 9 months. 2 companies designed, tested, and began manufacturing 2 different propeller designs. Republic Aviation modified production lines at 2 factories. The Army Air Forces developed new maintenance procedures, trained mechanics, and shipped thousands of propellers across the Atlantic. No single aspect was revolutionary. The achievement lay in speed and scale of implementation. The United States identified a critical deficiency and corrected it faster than Germany could develop countermeasures. German aircraft designers possessed technical knowledge to create similar improvements. Both Messerschmitt and Focke-Wulf employed experienced propeller engineers who understood theoretical benefits of increased blade area. But Germany's war economy in 1944 could not support rapid modification programs. German aircraft production operated at maximum capacity, focused on producing existing designs in sufficient quantities to replace combat losses. Introducing new propeller designs would require retooling production lines, recertifying aircraft performance, updating maintenance manuals, and training mechanics. Production disruption would cost thousands of fighters when Germany desperately needed every aircraft. Germans were trapped by strategic situation. They needed to match American improvements, but could not afford the production disruption required. This highlighted fundamental differences in American and German approaches to aircraft development. American designers accepted good-enough solutions implementable quickly. The paddle blade propeller was aerodynamically less efficient than more sophisticated designs. It created more drag than narrower blades at high speeds. It was heavier, requiring reinforced hubs and pitch control mechanisms, but it solved the immediate problem without requiring years of development to optimize every parameter. German designers often pursued theoretical perfection at the expense of practical implementation. German propeller designers worked on advanced variable pitch systems that would theoretically outperform crude American paddle blades. But these advanced designs existed primarily on paper, never reaching operational service in meaningful numbers. By March 1944, the paddle blade Thunderbolt had become the standard American escort fighter in Europe. The aircraft was no longer a compromise platform, awaiting replacement by longer-ranged P-51 Mustangs. The Thunderbolt had evolved into a formidable air superiority fighter, dominating German opponents in most combat situations. The psychological impact was significant. American bomber crews who had watched helplessly as German fighters climbed away throughout 1943 now saw enemy fighters chased down and destroyed in climbing combat. German pilots, already demoralized by increasing American numerical superiority, faced a tactical environment where their advantages had been neutralized. The Focke-Wulf 190, designed to be superior to the Thunderbolt in nearly every performance category, found itself matched or exceeded in the one area where it maintained clear superiority. The Messerschmitt 109 could no longer rely on vertical maneuvers to escape combat. German fighter losses climbed steadily through spring 1944. Many veteran pilots who had survived years of combat were shot down by Thunderbolts they thought they had successfully evaded. The full impact became evident during preparation for D-Day. Throughout May 1944, American fighters conducted intensive operations aimed at achieving air superiority over France. Thunderbolts ranged across northern France, attacking German airfields, destroying aircraft on the ground, and engaging any Luftwaffe fighters that attempted interference. Paddle blade-equipped P-47s proved especially effective in these fighter sweeps. When German fighters scrambled to intercept, they typically climbed from lower altitudes to reach American fighters operating at 20,000 to 25,000 feet. Thunderbolts could now dive on these climbing German fighters, attack, then climb away before Germans could retaliate. June 6, 1944. As Allied forces stormed Normandy beaches, Thunderbolts provided air cover throughout the day. German fighters that attempted to attack the invasion fleet or support German ground forces were consistently intercepted and destroyed by paddle blade-equipped P-47s. The Luftwaffe managed fewer than 100 sorties over invasion beaches during the critical first 24 hours. American fighters flew more than 8,700 sorties during the same period. This overwhelming superiority was possible because American fighters achieved kill ratios of 4-to-1 or better. The paddle blade propeller, by eliminating the Thunderbolt's primary weakness, contributed directly to achieving air superiority that made invasion possible. Statistical evidence supported what pilots experienced. In first quarter 1944, before paddle blade propellers became widespread, American fighters in Europe achieved overall kill ratio of approximately 1.8-to-1 against German fighters. By second quarter 1944, with most American fighters equipped with paddle blades, kill ratio improved to 3.2-to-1. By third quarter, it reached 4.6-to-1. These improvements cannot be attributed solely to propeller modification. American numerical superiority was increasing, pilot training improving, and Germany fielding inexperienced pilots to replace mounting losses. But combat reports make clear that improved climbing performance played significant roles in these victories. The Curtiss Electric C-542s paddle blade propeller, the most widely used variant, featured 4 blades with 13-foot diameter. Each blade had significantly increased area compared to narrow blade predecessors. This substantial increase translated to dramatically improved thrust at low airspeeds. The Hamilton Standard Hydromatic paddle blade, fitted to later production P-47s, offered similar performance with operational advantages. The Hamilton Standard design used hydraulic pitch control that was simpler and more reliable than the Curtiss Electric system. Total blade area was nearly identical, and combat performance was indistinguishable. Manufacturing effort required to equip the P-47 fleet demonstrated American industrial capacity operating at scale. Both Curtiss-Wright and Hamilton Standard produced thousands of propeller assemblies between June 1943 and December 1944. Each consisted of 4 blades, hub assembly, pitch control mechanism, and mounting hardware. Blades were forged from aluminum alloy, machined to precise airfoil shapes, and heat-treated for maximum strength. Each blade required approximately 14 hours of machine time, not including raw material preparation and finishing operations. Distributing these propellers to operational units in England presented logistical challenges. Each assembly weighed approximately 650 pounds and required careful handling to prevent damage during shipping. Propellers were packed in wooden crates with protective bracing and shipped across the Atlantic on cargo vessels. Voyages typically required 2 weeks. Upon arrival, propellers were transported to air depot facilities where mechanics installed them on aircraft. Installation required approximately 16 hours per aircraft, including removal of old propellers, installation of new ones, rigging pitch control systems, and conducting ground tests. Between January and June 1944, air depot mechanics in England retrofitted over 1,000 Thunderbolts while maintaining operational readiness of frontline fighter groups. Tactical evolution of paddle blade Thunderbolt operations continued through summer and fall 1944. Pilots developed increasingly sophisticated techniques to exploit improved climbing performance. One particularly effective tactic was the vertical scissors, where 2 Thunderbolts would engage a German fighter in climbing dogfight. As enemy aircraft climbed to escape one P-47, the second would position to attack as soon as the German fighter lost energy and could no longer climb effectively. The German pilot faced an impossible choice: continue climbing until stalling, making him easy target for the trailing Thunderbolt, or roll out to maintain airspeed, allowing the lead Thunderbolt to execute diving attack. Another significant development was use of paddle blade Thunderbolts for low-altitude ground attack missions. Improved thrust at low speeds allowed heavily loaded P-47s to maintain speed and maneuverability, even when carrying 2,500 pounds of bombs or rockets. Pilots attacking German ground targets could enter attack dives from lower altitudes, reducing exposure time to anti-aircraft fire. After delivering ordnance, paddle blade-equipped Thunderbolts could climb away from target areas more rapidly, again reducing vulnerability. Between April and September 1944, Thunderbolts flew more than 88,000 ground attack sorties, while suffering approximately 820 losses to all causes, a loss rate of less than 1%. The versatility of paddle blade Thunderbolts allowed them to remain in frontline service even as longer-ranged P-51 Mustangs became available. Many fighter groups chose to retain Thunderbolts specifically because improved performance made them exceptionally effective in multiple roles. The 56th Fighter Group, commanded by Colonel Hubert Zemke and later Colonel David Schilling, flew Thunderbolts exclusively throughout the entire war, despite opportunities to transition to Mustangs. The group's pilots believed the rugged construction and 8-gun armament combined with excellent climbing performance provided by paddle blade propellers, made it superior to the Mustang for their operations. German fighter pilots who survived the war consistently mentioned the paddle blade Thunderbolt as one of the most capable American fighters they faced. Major Günther Rall, who survived with 275 victories, noted in post-war interviews that improved Thunderbolts were far more dangerous than earlier versions. Rall stated German pilots had to treat paddle blade Thunderbolts with the same respect they accorded P-51 Mustangs, recognizing the American fighter could match German performance in most combat situations. Engineering lessons learned from the program influenced American aircraft development throughout the remainder of war. Rapid development and deployment demonstrated that incremental improvements to existing aircraft could often provide better value than developing entirely new types. The P-47 itself benefited from continued improvements beyond propeller modification. Water methanol injection systems increased engine power to 2,535 horsepower for short periods. When combined with paddle blade propellers' improved thrust characteristics, this further enhanced performance. The P-47M, introduced in late 1944, incorporated both modifications and could climb rapidly, matching or exceeding climbing performance of any German fighter. The financial investment required to develop and deploy paddle blade propellers was modest compared to operational benefits achieved. Development costs for both Curtiss and Hamilton standard propellers, including wind tunnel testing, prototype construction, and flight testing, totaled approximately $3 million. By comparison, developing an entirely new fighter aircraft would have cost at least $100 million and required 2 to 3 years before reaching operational service. The paddle blade propeller represented exactly the kind of cost-effective improvement that made American air power difficult to match. Paddle blade propellers also highlighted importance of feedback loops between combat operations and aircraft development. Problems with narrow blade propellers were identified by frontline pilots who filed after-action reports describing German fighters escaping through climbing maneuvers. These reports filtered through intelligence systems to reach engineers who could diagnose root causes and develop solutions. This feedback loop operated relatively quickly, with problems identified in combat leading to engineering solutions within months. German forces had similar feedback systems in theory, but found them increasingly disrupted by chaos of Germany's deteriorating strategic position. Strategic impact extended beyond direct air combat. Achievement of air superiority over Europe, to which improved Thunderbolts contributed significantly, allowed Allied ground forces to advance with minimal interference from German air power. During breakout from Normandy in August 1944, American ground forces advanced under umbrella of air superiority, maintained largely by Thunderbolts. German ground forces attempting to retreat or reposition found themselves under constant attack from Allied fighters. Improved climbing performance meant German fighters that attempted to interfere with ground attack missions could be quickly intercepted and destroyed by escorting P-47s. The final major air combat involving large numbers of paddle blade Thunderbolts occurred during Battle of the Bulge in December 1944 and January 1945. When German ground forces launched surprise offensive through the Ardennes, bad weather initially prevented effective air operations. When weather cleared on December 23rd, Allied air forces launched massive attacks against German ground forces and supply lines. Paddle blade-equipped Thunderbolts flew hundreds of sorties daily, attacking German armor, trucks, and artillery positions. Luftwaffe fighters attempted to interfere, but were consistently driven off by escorting P-47s. By February 1945, organized Luftwaffe resistance over Western Europe had effectively ceased. German fighter units were being withdrawn to defend homeland against increasing strategic bombing campaign. Paddle-blade Thunderbolts had played significant roles in achieving this air superiority, though their contribution was overshadowed by more glamorous reputation of P-51 Mustangs. Military historians examining the air war have sometimes downplayed the Thunderbolt's importance, noting P-51s achieved more aerial victories and flew deeper into Germany. But this misses the critical point that Thunderbolt's transformation through paddle-blade propeller modification came at a crucial moment when German fighter forces still represented formidable threats. Between January and December 1944, Thunderbolts were credited with destroying 3082 German aircraft in aerial combat while losing 824 P-47s to all causes in European theater. This represented overall kill ratio of 3.7 to 1, comparable to or better than other American fighter types during same period. More importantly, Thunderbolt's transformation from mediocre climber to capable vertical fighter occurred during period when such capability was most desperately needed. Post-war fate of paddle-blade Thunderbolts reveals how quickly wartime innovations can be forgotten. As jet fighters entered service, propeller-driven P-47s quickly became obsolete. Most surviving Thunderbolts were scrapped or sold to foreign air forces. Technical achievements that made paddle-blade Thunderbolts effective fighters were eclipsed by revolutionary capabilities of jet propulsion. Few pilots who flew improved Thunderbolts in combat went on to positions where they could ensure propeller modification received proper historical recognition. Yet paddle-blade propellers represent fundamentally important type of military innovation deserving greater recognition. It was not revolutionary breakthrough that changed fundamental nature of air combat. It was evolutionary improvement that took an existing platform and eliminated its most critical weakness through relatively simple engineering. This type of innovation, less dramatic than revolutionary new technologies, but often more immediately impactful, characterized much of American military success during World War II. Ability to identify problems, develop practical solutions, implement solutions rapidly, and deploy them at scale gave American forces decisive advantages. Engineering principles underlying paddle-blade propellers remain relevant to modern military aviation despite transition to jet propulsion. Fundamental insight that blade area must be optimized for intended operating conditions rather than theoretical maximum efficiency applies to turbine blade design, helicopter rotor design, and unmanned aerial vehicle propulsion systems. Military engineers still face challenge of balancing multiple performance requirements across different flight regimes. German perspective on paddle-blade Thunderbolts provides sobering lessons about consequences of industrial and strategic weakness. German engineers understood propeller theory as well as American counterparts. German aircraft factories were capable of producing improved propellers had they been given resources and opportunity. But Germany's deteriorating strategic position, resource shortages, and increasingly disrupted industrial base made rapid improvement programs impossible. Paddle-blade Thunderbolts succeeded not because American engineers were more skilled, but because American industry could support rapid innovation while German industry could not. Wars are not won by single wonder weapons or brilliant strategies or revolutionary technologies. They are won by accumulated weight of thousands of incremental improvements, each addressing specific problems, each implemented efficiently, each contributing to overall superiority. Paddle-blade propeller was one such improvement among many, but it came at a critical moment when German forces were still capable of contesting Allied air superiority. By eliminating Thunderbolt's primary weakness, the modification helped establish air dominance that made invasion of Europe possible and accelerated Germany's defeat. This achievement, born from mundane work of propeller engineers rather than dramatic exploits of fighter pilots, deserves recognition as one of decisive technological contributions to Allied victory in Europe.